Hello, everyone. We are live. We've got a lot to talk about. We've got Sarah on the call. We're going to dive straight in. Sarah, would you want to introduce yourself?
Thank you. So first of all, it's exciting to be here live. I'm hoping that we'll keep it interesting. People will be sending questions through. So a little bit about me is that I'm a researcher at Google Brain. I do research on machine learning, specifically on how do we train models to fulfill multiple criteria. And I'm interested in interpretability, robustness, model compression. I proudly I'm here, I guess, in large part because I met Anita last year in Nigeria, and I grew up in Mozambique, South Africa, Swaziland, Lesotho, Kenya. But it was my first trip last year to the Lagos office, and that's where we hit it off. And so I'm very thrilled to be here.
Awesome, Sarah. So we're diving straight in, and you're going to have to do 3 definitions. They may be textbook definitions, but we prefer personal definitions, right? So what do you understand by machine learning?
So machine learning is learning from past experience. So humans do this quite well. For example, you may have a friend that you've met in the past, and every time that they've met with you, they've been late, maybe 15 minutes late, maybe 20 minutes late. So what happens next time you schedule time to meet with them? When do you arrive? This is a question for you. Yes, so you correct answer. And in fact, what that demonstrates is learning from past experience. You know they've been late in the past, so you adapt your behavior. We want to do that with machine learning models for perhaps much more interesting questions than estimating when people are late. We want models to be able to identify objects based on seeing those objects multiple times. And we want models to be able to explore the world. So that's what machine learning is. We don't tell the model exactly what they do to do. The model learns it based on past experience.
Okay. Now, usually when people start getting into machine learning and more like the focus of today's webinar, which is deep learning, we see these 3 concentric circles where you have artificial intelligence, then you have machine learning, and then you have deep learning. So what is deep learning and why go deep? And then in the broader context, what is artificial intelligence? And like I said, we're not so much interested in textbook definitions. We're more interested in those when will your friend be late definitions. So maybe we should go back to AI, and then you can now come back to deep learning.
So AI is really, we have to go back to the 1940s. So AI is this idea when the first conference happened, which was the Dartmouth conference in 1945, or perhaps 1946. Someone should spot check me if you're on your computer right now. But that conference brought together really famous researchers who were interested in the question of how do we make machines behave or have skills that are normally reserved for humans. Things like sight, things like hearing, things like being able to combine audio, visual, textures, and be able to make informed decisions about the world. Now that's quite ambitious. And in fact, a lot of machine learning and deep neural networks have focused on just trying to achieve performance on a subset of those tasks. And perhaps I can segue into the definition of how deep neural networks differ from machine learning, but they're really a subset of this overarching goal of what makes us able to take in all the information of the world and make it useful. Because in fact, humans are very good at condensing a lot of information. When we navigate the world, there's so many things that we could pay attention to, but we're very good at paying attention to the important things to make a decision. And that's what we want to try and figure out with AI. Should I go on? Are we ready for the difference between deep learning and machine learning? I presume so, from the silence.
Yeah, so, always ready.
Okay, excellent. Yeah, let me say, so, I kind of told you about AI and this overarching goal of we really want to think about how these skills can be imparted. Machine learning is really this idea of how can we train models that are able to generalize to unseen data? And the difference between machine learning and deep learning is really the degree to which we specify exactly what the model does. So early efforts in computer vision, and this is a very good example. So early efforts in computer vision that were not deep neural networks told the model exactly what type of features to extract. So you would have something like a Sobel edge detector, and all that does, if you have a photograph, it picks up the edges or the contours of the object. And that was then passed into a model. It was very explicit. You knew exactly what it was going to extract. And then after that, you apply a linear regression. Compare that to deep neural networks. So we go to convolutional neural networks, and in fact, we don't tell the model exactly what to extract. We kind of leave it up to the model to learn what are the most useful pixels to figure out the task of what the object is. And so I would say the key difference is we've kind of given up control. We no longer know what the function is explicitly. All we know is that we've set a task and we've allowed the model to learn through feedback. Whereas other machine learning approaches, it's much more explicit what we're telling the model to extract.
So we have a question here from Nigeria, and it says, will you define it as deep neural networks? And I get that sometimes even when I'm trying to process it. What is deep neural networks? What is deep learning? Are they sort of like synonyms, or do they slightly mean technically different things? And sometimes this technical difference often doesn't matter, like programmer versus coder versus, software engineer versus application developer. People have these sort of debates and arguments. But if you want it to be, I would say, technically correct, deep neural networks and deep learning, is that?
Doesn't matter. There's things we care about, and there's things that are okay to fudge, right? Like deep neural networks are really this like class of deep learning approaches. And within deep neural networks, you have different networks. So you have something like a convolutional neural network, a feed-forward network. A feed-forward network just means the same as you just don't have a convolutional filter. So it's your simplest type of, you just have a hidden layer. And broadly, all these networks are just referring to networks where you have some type of nonlinear activation function, which means we're no longer completely specifying what the model learns. We're leaving it up to the model. The model learns a high dimensional space, which is useful. But yeah, don't stress it. They're pretty much the same thing. And no one's going to say, oh, you don't know about machine learning if you switch the two.
Okay. So now this is the point where I go back to your website and read your bio, copy and paste it for this video, and then I stop at a specific line that says, not the line that says you were born in Southern Africa and you've been around the world, or around, not that line. The line I'm talking about right now is, Sara taught herself machine learning. So you taught yourself the difference between deep neural networks and deep learning and machine learning and AI? Okay, let's scratch that. The question now is...
Rewind.
Okay, the question now really is, most times when people interact with these products or with these technologies or these phenomena, right, it's usually with a product, so you signed up for Facebook some days ago and then someone tells you you've been tagged in a picture, you should go check if you actually are the one there, So picture tagging, finding photos, a reminder from 2 years ago, some amazing things with translation, your Uber or something turning up in exactly 20 minutes when they said it was going to get there in 20 minutes, and then you trying to get to the airport in Lagos, and you know that there's like 200 factors that could delay you, and somehow your ETA, estimated time of arrival, is pretty accurate, like 30 minutes is 31 or 29 minutes. Most people interact with AI, deep learning, machine learning through a product or a service or maybe a tool, and that goes on to excite you to get into the field, right? What products with AI or ML really blow your mind, or what really tipped the scale for you? Or like, okay, this is so amazing, I need to go find out more about this and teach myself machine learning?
So it wasn't a product for me. It was actually, so I guess there's two stages. There's machine learning, what triggered that, and then there's deep neural networks, which was a separate like aha moment. So for machine learning, it was that I was working at the very beginning of my career, my first job. I was also volunteering at the weekends working with nonprofits. And their data was so messy and so interesting and was real world data. And I trained as an economist. And so a lot of my first interest in machine learning was I just wanted to have more powerful tools to deal with real world data. Like economists love linear models, mainly because economists, if you've done economics, it's all about having assumptions about the world and being able to know the distribution of your data. But that often doesn't translate to the real world. So a lot of where I was initially really, really interested in learning more was just how do we model real world data? There was a second point, which is, I think, the real instant moment where I listened to a podcast, and it was a podcast which was about the history of, in particular, deep neural networks. And this was, it must have been in 2015 maybe, or maybe 2014. But what it described was how recent the history is. And it was talking about how really all this modern computing is not that old. It's like when we think about the first computer, it's like 1950s. And then when we think about the efforts to make deep neural networks work, it only started working in 2012. And it just hit me. This is history happening during my lifetime. This is history that I can be part of. This is not established technology. This is like what I imagine of the first people who participated in a gold rush is like. It's just, it is history that you can like carve and be part of. And so overnight, I was like, I want to know more about this, that this is so recent, but has accomplished so much already and has such a huge impact on technology. And that was what I call the brute force stage in my career, because literally overnight, I decided I want to work on this, and probably I want to work on this for the rest of my career. I think you're muted.
Very, very interesting. I need a deep neural network to let me know every time I'm muted or not muted. So the next question, which is sort of like a segue into this deep learning, machine learning, and it's usually something a lot of people struggle with. And sort of fortunately, someone has asked that question. I always love this being very engaging, which is, can you talk to the math needed behind ML and DL? I find that having the right math and stat background will make you a better machine learner. There's usually also another perspective to this is, do I need to have very deep, discrete math background to get into machine learning? We've had a host of answers over the last couple of episodes, and there's a lot of answers out there on the internet. But usually what people cannot distinguish is what career paths in the AI or ML space can I still take or can I still choose if I don't have a very strong math background? And then if I really decide, for instance, like no aha moment that I want to go into deep learning, maybe it's probability, maybe it's statistics, maybe it's calculus. What is the math requirement? So it's a two-part question. If you don't necessarily have all the math background, what are all the career, or what are some of the career options that exist in the space? And then if you do want to go into a very math-heavy career option, like deep learning, which I guess should be heavy in some mathematics, what sort of knowledge or what sort of math specifically should you try to brush up on?
Yeah, so I'm not surprised that there's been a high variance in answers to this question, to be honest, because I guess it really depends on who you talk to. I mean, academics tend to be quite attached to their mathematics because I think that particularly machine learning conferences for some time have been quite math heavy. Here's what I think, which is probably probably a more nuanced opinion. Where I've seen people succeed in machine learning is that there's three buckets. So being, and this in fact, I think applies to both applied machine learning as well as research machine learning. And I've done both. So I worked in a startup as a machine learning engineer, and I've done research. And I think the same three buckets apply, surprisingly. which is that one, you want to have a very strong technical foundation. And that's because you just have so much more control if that's the case. Like, if you're able to really be able to build models, deploy models, and understand various deep learning stacks, it gives you a lot of freedom to experiment with your ideas. And so I always encourage people, particularly at the beginning of your career, focus on building your technical skill set, and it will pay a lot of dividends later. The second piece is actually, I think, very underrated, which is creativity. Like, for example, in applied, a lot of applied machine learning is still feature engineering. You know, we're not deploying deep neural networks a lot of the time in resource-constrained environments. I hope that we eventually are able to. That's partly why I'm working on model compression. But right now, a lot of it is still feature engineering. Can you craft good features? Do you identify patterns in the data? Do you understand this domain? And that needs creativity as well as it needs expertise in the subject matter that you're trying to model. And then the third bucket, I would say, is mathematics. So mathematics is often useful because what you don't want is you don't want people who are simply importing libraries and don't know the underlying model components. And the reason why is that often there's assumptions in what models should be used for what types of data distributions. And if you don't have an understanding of what the underlying mathematics are, then you may not anticipate failure points. That being said, the mathematics for these models, and particularly models that are widely deployed, tend to be, they're not, I mean, it's not Albert Einstein. It's not, you know, if you talk to a physicist, when they come to ML, they're often bored. And the reason why is that it's particularly models that need to scale are really based upon fundamental notions of statistics. I think that focusing on core algorithms and understanding the mathematics behind those algorithms is a good way to start. So looking at clustering algorithms, understanding the mechanics there, even trying to code an algorithm from scratch will give you a really good understanding of the mathematics behind it. And then you have things like decision trees and SVMs. Those are all really important just to understand what are the core components behind it. But that being said, when I talked about the three buckets, what's interesting is that my colleagues at Brain, they're not equally good at all three. In fact, it would be kind of puzzling if they were, because it's such a weird combination. And in fact, what people tend to do is they get very good at one, and that becomes their contribution, and they're good enough in the others that they can really pair with other people that are better. So a lot of it is about knowing your strengths and focusing on amplifying those strengths and knowing the foundations of the others.
Okay. Know your strengths and know the foundations of the others. So let's speak a little bit about your strengths, right? And now that you have a lot of focus in deep learning, there's fundamentals of deep learning. I think deep learning sort of finds itself in use in like two broad areas, which is like two prominent areas, like computer vision and natural language processing, right? So like, can you just tell us a little bit more about, would I even say, the fundamentals of deep learning? Just like, I mean, you've touched on it a lot, but like sort of like a wrap up of that. And then where's the future of deep learning? What happens next? Are we going to see another technique or approach to model optimization or to model definition? Is it going to be a different thing? Or do you think there's still a lot within deep learning that is yet to be discovered?
Yeah, wow, the hard questions. So this is why we're doing this live. I see what's going on. So firstly, let me tell you a little bit about the research I work on, because maybe that will provide some context for the answers I'll give about the future. But so I've been very interested in how do we train models, not just for test and accuracy, but for other things. So we want it to be interpretable, or we want it to be fair. We want it to be compressed. We want it to work in resource-constrained environments. So a lot of my work has been about, if you have multiple criteria for your model, how do you achieve that? What are good objective functions? And so I would say that in many ways, because going back to those three buckets, and I think you were hinting at what is my strength. I think a lot of my strength is I've thought a lot about how to unify some of these subfields. So a lot of researchers take two approaches. Like either they stay in a subfield for a very long time and they specialize in one element of that, or researchers tend to sample and see connections and pair ideas in different ways. The second approach is a little bit riskier and it takes longer, right? Because you're specializing in multiple areas, but it often provides unexpected benefits. So I would categorize myself as the second type of researcher. For example, my latest work has been about how do we connect compression to interpretability? Can we leverage models compressed to different amounts of sparsity to surface examples of models uncertain about? And that's actually kind of a connection made between two different subfields. Your question, which is probably getting to the meat of this wider view, is what is next? So what is the future? And to answer that, we kind of have to look at where we are. So I think there's two different answers for the applied domain and the research domain. So for the applied domain, in many ways, we're at the beginning, right? We have deep neural networks, which we know perform far better than other model approaches for certain tasks, but it's really hard to launch them. And I would say it's quite painful right now in terms of applying them to real world domains. Also, there may not be the interpretability that people like. So often people, when you approach someone in an actual business use case, they often still prefer a decision tree because they want to know exactly what the feature importance is. So there, I think there's so many opportunities. It's almost as if we just got started. For example, number one, how do we make these models work in resource-constrained environments, right? The communities that I grew up in are often energy constrained. So you have your phone for the day. You don't know if you can recharge it at a different point in the day. You're connectivity constrained. So you may have Wi-Fi, but you may go to a location with no Wi-Fi. And data is really expensive. So those three mean that if we think about launching deep neural networks and making them accessible, we really have to think about how to make them work in low energy, low latency environments. And that's an area of research that I'm really excited about. And I feel like that's wide open. There's so much to do there. And I suspect a lot of it's going to be, how do we make these applicable? And also, how do we make these robust? Like, how do we prevent the kind of failure points that we see with deep neural networks where the model is trained on a certain data, and then if you add noise to the test set, it dramatically fails all of a sudden. There's things like that that researchers are really grappling with, but it's also an applied problem. We just need software engineers to make better packages, to better compress. And that's why I see a huge opportunity for software engineers who are just optimizing things like from the compiler stage of the hardware through to packages themselves. Like interpretability, a big obstacle right now is how do we just make it easier for people to use interpretability tools? There's a second answer, and this is the research answer. So the research answer is really based on this ultimate goal. We went back to the 1940s when we talked about what is AI, and the ultimate goal of artificial intelligence research is still to try and create machines that think like humans and do skills reserved from humans. And from that, what do we learn about how we think about the world? And for that, I think the major obstacle is going to be how do we scale? So right now we're using bigger and bigger networks. So for example, GPT-3 just came out and that cost $12 million to train for a single model. And so that was an impressive, thank you. Yeah, I had yeah, excellent facial response. But that's not scalable, right? I mean, it's interesting because what the authors of that research showed is that there's still a doubling of return for parameters. So it's still a linear slope, which means we're getting bang for our buck when we train these ever larger models. But the question really is, where are we? Which is that we're still nowhere near the intelligence of a 4-year-old child. And that even though we're in this huge regime of massive models, we may need an entirely different, more efficient algorithm to make the leap to human level intelligence. And that's difficult because right now it's a divided field. Some researchers think that the strategy should just be scaling. So just throwing, let's go to 24 million. And other researchers think we need to revisit the foundation itself. And we just need a different model, which doesn't require us to throw so much compute at the problem, which tends to be what's happening now.
Okay, so we've talked a little bit about the fundamentals. You've given us this opinionated view about the future we should expect. I think for a lot of people on this webinar, and this is not a machine learning conference, it's not NeurIPS or one of these conferences, this is the worldwide wild web, right? So everyone is here, everyone who's either had a buzzword, struggled with learning machine learning, dropped out of a nano degree, attended some meetups and couldn't get it. I saw someone who put up a comment, I think, if I can find that, he asked a question that I don't understand. I need to Google the question to figure out if I can, but I'll put it up and then I'll hide very quickly. So it's talking about ReLUs and functions. But one big question, one big reason why we put this webinar series together, or we've evolved these webinar series, is really to hear from people or from practitioners in the field. How do you get started, right? There isn't any one perfect, correct way, but we feel that by sampling a number of opinions and by people trying to identify maybe a practitioner who's gone before them and has kind of like a similar trajectory, maybe you didn't come from a CS background, maybe you lived in a resource-constrained area and that excited you, and then you overcame some challenges to go on to build this career. We really want to get some very opinionated advice. Like, how do we go about, or how would you, if you were to advise your former self from maybe 10 years ago, you write a letter back to yourself and like, this is an easier path or a better way to build a machine learning or an AI career. Don't sweat this stuff, major on the major things, minor on the minor things. What would be your advice to people who are either getting started with machine learning and deep learning, or those who are already in the field, but are still struggling to either find their first job, their first gig, and they're wondering whether a machine learning career is really that promising as it is? I don't know. So how would you advise people to build an ML career, whether it's research or whether it's applied?
Yeah, no, this is an excellent question. And I'm sure it's also high variance in answers. So a little bit of context. So as you know, as was mentioned, I am self-taught. So I can talk about what worked for me, but I actually think it's more elements of what worked. So I think self-taught is very lonely. So first of all, congratulations for being here. I believe it's 4 p.m. right now on a Friday. So you're already doing really well by attending this webinar. And I think that it's very important to take the small steps, and it's very important to have the accountability of being in some type of community. But there's a wider question of how do you even get started with a body of knowledge? So one is focus on a problem. There's too much knowledge out there. There's too many online courses. There's too many possible ways to just study or skim without learning. It's really important to choose a problem. And ideally, it should be a problem where you're accountable for a solution. The tricky thing about a Kaggle competition is that Kaggle is an amazing resource in terms of it creates competition incentives. But if you're starting out and you're not winning or on the leaderboard, it's also very easy to just say, oh, I tried, and then, drop out. I would definitely say, look around you. What problems need solving? Is there something that you can do? Is there a community that you can do? But focus on solving a problem for an actual stakeholder. And that doesn't have to be that you find a job. Like, for example, when I mentioned why I first got interested in machine learning, I was working with nonprofits. And so I was really learning the craft, in particular, starting to learn a lot of the engineering skills I have by just volunteering with different nonprofits. The second thing is that as soon as possible, that should transition to your full-time job. And the reason why is that some of the biggest career accelerants happen when you're not just doing this before work and after work. That's fine at first because you have to just hustle enough to be able to get someone to take a chance on you. But the sooner that you're able to translate that into someone saying you can do this full-time, the better, because that's where you really see the leaps and bounds. I think the third important thing to realize is that this is not overnight. This is a brute force effort. I would say that, so it depends your starting point. If you're starting with no engineering skills, I think the convergence point for you to be as good as engineers at a place like Google or Facebook is if you do it for 4 years, and it's like any language, you then become fluent in it. And I think thinking about that, don't expect to compare yourself to the next person. It is a brute force effort. Like, you're learning a craft. And whenever you're learning a craft and you're learning to become an expert in your craft, it takes time. And that is the thing that you have to say to yourself as well, because it's a combination of dedication, choosing problems where you are accountable so you can measure progress, as well as kind of, are you passionate about this, right? Because the trickiest thing, I think, when you're sampling a lot of different fields, if you don't feel an immediate gut reaction, that's okay. But after 6 months, 8 months, if you're still not sure, then pause and say, I think the other tricky thing I see is where people are forcing it, and that could be because they didn't have a good introduction, but also just if you're passionate, a lot of it will pay out over time. A lot, for example, I think a lot of the reason I was able to get through that brute force self-taught period, which is really lonely, is that I was just so eager. Like, I just knew that regardless of whether I ended up at Google or somewhere else, I'd probably want to do this.
Thank you, Sarah. So before I step away from this question, I've seen a lot of really positive comments about the advice you've given and the way you've sort of like framed it. We will do a little bit of a wrap up with a familiar face on our podcast or webinar, and it's an interesting question. Here he goes. What's the worst advice you've seen given or heard in the ML field?
So it depends again. So I think there's two. So I'll do applied domain and then I'll do research domain. So I think the worst advice we've seen given or heard in the ML field is, I see this often, which is people really interested in like flashing how complex their model is. And the truth is, most real-world problems don't need that much complexity. And by complexity, I mean, a lot of people want to think of everything like a Kaggle competition. Everything has to be a deep neural network. Everything has to be ensemble approaches. And the truth is, a lot of real-world problems, you just need to have good hypotheses, know your data distribution, explore, do some feature engineering. Don't jump straight to a deep neural network. So that's the applied domain. I think in the research domain, the worst advice is to just publish, because I think a lot of researchers tend to just go for conferences and churn out papers and don't stop to think, am I working on an important problem? Kind of going back to that division between researchers who just focus on a single direction versus just sampling and thinking about, am I working on something that actually, if it worked out, would be an important development in the field? And I think that publishing often creates the wrong incentive structures. It forces you to iterate on small contributions rather than take a step back and think about what's important.
Thank you, Sarah. I will just quickly look at any other questions that we may have here. Okay, there's one question. Let's go back to the ReLU function thing. And I can't answer this question. You probably can, maybe you can, I don't know, but here it is.
Talk of ReLU function. I want to put you on the spot now. If you can answer it, I want to see, let's see this happen. So talk of ReLU function. Everyone says it's the best. What would happen if it causes bias and weights some misbehavior? Can it learn and rework the network? Why ReLU? Okay, excellent question. Spotlight, over to you.
So the essence of this webinar is really just, Sarah, bye.
Oh, so yeah. Okay, it's actually back to me. I see what we're doing.
Yeah, thank you. Am I allowed to Google the answer and paste it back in the box? Like, what? Okay, let me do a YRELU and I'll figure out what I come up with. But okay, in the meantime, why don't you just go ahead and tell me YRELU?
Okay, so so actually it's a very good question, because on surface level it looks quite simple, but it's actually quite complicated to answer. And the truth is the following, is that ReLU is actually a secret ingredient that started to make deep neural networks work. Before that, a lot of the activation functions, such as sigmoid or 10H, like a lot of them cause issues with gradient flow. And when we talk about gradient flow, that's literally how signal passes through the network. So it's all the pixels of an image being passed through the network. And it's how the feedback from the correct label matched with whatever the model predicts goes back. So we want good gradient flow because we want all the weights to be updated. And bad gradient flow looks like gradient saturation. It's called, or it's often called gradient saturation. It's where the gradients explode, and so you have these massive gradients, or where they're too small, and so the weights go to zero. And the issue with earlier activation functions is that it caused a lot of instability. It caused a lot of this gradient saturation. And ReLU turned out to be really good. And ReLU is kind of baffling because it's so simple, but ReLU turned out to be so good at just allowing good gradient flow. What's interesting about this is that the story has changed a little, because now we have batch normalization, and batch normalization kind of controls gradient flow because it uses statistics on the batches themselves to bound the activations. And so it's again unclear whether we can return to some of the ideas around these early activation functions and bring them back in the loop. And a lot of us have just gotten so used to using ReLU, and it works so well. There hasn't really been a lot of investigation there. There have been variants of ReLU introduced. So I believe there's activation function called ELU. And there's another activation function that's some combination of ReLU and something else. So there have been like a family of ReLUs. But the standard ReLU tends to work quite well right now. So I hope that was a good stab at that question.
Great stuff. Great stuff. Now the next question is for you, and if you don't get this question, we may have to end this webinar.
The stakes are so high.
No pressure.
I like this. Can I call a friend if I don't get it? Is it that type of show?
Okay. So I'm going to show the question in 3, 2, 1, and you're going to either agree, disagree, or give an answer or an opinion. 3, 2, 1, boom. Oops, wrong question.
Oh, drug dealer.
That was definitely not the question. Where is Bethan's question?
Oh my goodness. Yes, absolutely. Yes. I mean, I feel like this is a version of a TV show. You've already got your audience. So, I mean, that's a question I'll put back to you. What's the hiccup? Is it your agent? I can be your agent. I can try and, suss out what's happening. Who needs it's interesting because I heard rumors that Netflix is looking for a machine learning talk show. So not that I know anyone there, but I think that would be a good venue for this type of thing.
I'm just a bit worried that you used the word agent, because now I will go back to one of our questions from a previous webinar. How am I sure you are actually you? And I'm not talking to like a projection or hologram or a simulation of you. Is there any way you can prove to me you're actually on this webinar?
What? You would ask me that? We go way back.
Okay.
No, I get what you're asking. You're asking the ultimate question, right? And this question actually started in the 1940s as well, because Turing published a paper which was all about the Turing test as we now know it, which is, can you tell the difference between a model and a human trait? And often this is applied to language. So the first Turing test competitions, there was actual competitions where someone would send dialogue and you would have to chat with the bot and figure out, is it human or not? But your question is a good spin on that, which is, am I really me, or am I a projection? And there was an interesting answer to this question in a fantastic movie, which I love, which is Ex Machina. And in Ex Machina, the very last frame of the movie, the robot is alone. There's no humans around her, and she smiles. And that was seen as something where she was gaining humanity because there was no audience, and yet she still smiled, which was seen as something intrinsically human. Because if you're an agent or a bot, you're performing for an audience. You've been programmed for a specific objective. So it's a very interesting question.
Okay. Yeah. Another interesting question. Is this webinar recorded? I like the link from my brother. Yes, the webinar is recorded. It's going to be on YouTube live. It's going to be on YouTube on my channel. I think also on the Dev Communities Africa channel.
I've heard.
I haven't signed yet the Netflix deal. Once I sign the deal, I'm going to go back. Because actually, this is actually season 1, episode 8. So we're getting a very good cadence. Now, Sarah, I want to take a step back to, I think, something we've glossed over, first of all, in the intro to this webinar. And it's something that's really very important because for the researchers, the software engineers, even for business decision makers, even the general public, there's two things that I'm not very clear if I'm putting it the right way, but when I speak to someone like you, I hear of model interpretability, right? For models and at that level, you know what's going on, figure out what's going on, the algorithms and the rest. But even at the more executive level, where I'm a financial service provider, giving out loans, credits, yes, no, making such decisions, people talk about AI explainability. So it's almost like on a higher level, like how do we, so yes, you said you're going to put AI, and AI will make the decisions on whether I should give a loan or not, on whether I should pay an insurance claim or not. So I'm the CEO of a company. I don't know much about machine learning. I want you to be able to explain to me a little bit more what is happening in the background. So at that high level, there's this explainability issue about it has things to do with fairness, ethics, bias, and people want to really understand what is going on. And then when you go deeper, you're talking about model interpretability. And in that scenario, I think you're more talking to researchers and engineers and more applied people, even though that eventually bubbles up to like the CEO. So can you say everything about interpretability and explainability on the like the business and even the policy side?
Yeah, I mean, it's a very good question. So interpretability as a whole is, our goal is to just gain more intuition into a model behavior, right? So often that can be someone who's deploying a model who wants to make sure that the model is not going to fail immediately. They may want to know more intuition into what the model has learned. There's very famous examples, for example, in healthcare of models just learning that pictures of essentially malignant skin lesions are photographed along a ruler. So the model just learns the ruler is pictured amongst a certain type of skin lesion. And so when you deploy it, it fails because that ruler is no longer present in the photograph. So one reason is that we just want to anticipate what is the model actually paying attention to in its behaviors so that we can avoid issues once we deploy. The explainability is a subset of where we want to provide intuition, which is that when we deploy a model, often for end consumers, we want to provide an explanation for why we gave a certain prediction. So explainability is really focused on, let's provide an explanation, and it tends to be mostly focused on for a single example. So we have a single example, an image. Why did the model behave in a certain way for that image? But the question of when interpretability is needed and how people should pay attention to it, it really depends on a few things, right? It depends on, do you have a lot of historical data for this model? So have you seen this perform over multiple years? That may make you trust the model more despite not knowing the precise function, because you've just seen it perform in different environments and you have an understanding of the input-output. There's a second thing, which is a sensitive domain. So if you're deploying to healthcare, you mentioned financial institutions credit. It's far more important that we have interpretability because incorrect behavior can really damage human welfare. And so there we really want to have a better sense of what's happening. The third is if we would compromise another quality that we care about, like privacy. So for example, often people say for interpretability, just release the weights of the model, but that may contradict or jeopardize individual privacy. So there we may think about it differently. But interpretability is a really interesting field because right now there's a lot of exciting efforts to go beyond single explanations and surface what the model finds most challenging and most easiest to learn. And that's actually a different type of interpretability because it gives you a relative understanding of where the model struggled and where it's doing really well. And the reason why efforts in that area have been more recent is that we're just getting better at scaling computational expensive processes. Like estimating feature endpoints is quite expensive, particularly for computer vision problems. And now we're finding more clever ways to do it, which is really fun.
Okay. We're doing very well on time. And I think this has been a very interesting webinar. Like usually I usually say this almost like a cliche that after this, I'm going to just go back and play the webinar and watch it like an attendee. Really serious. I'm going to have to watch this one as an attendee because there's a lot of things that have flown over my head and I'm not taking enough notes. So I'll jump to a few questions that are coming directly from the audience. We can skip or we can answer very briefly. Depending, some of them are, I think sometimes people ask very specific questions.
I'm going to be in the mix again because I was intrigued. That flashed for a second and I was like, car in the drugstore.
No flashes. How do you deal with the problem of class imbalance?
Yeah, that's an excellent question from Blessings. So class imbalance is actually very typical of real-world data sets. So you can take a few different approaches. I dealt with this when I was doing my first ever engineering role at a startup called Udemy, and I was part of the data team, and I was working on fraud. So detecting whether reviews on instructor sites were fake or not. And there was huge class imbalance because fake reviews are a very small percentage of what is actually left on an instructor's course. So for that, there's a few things. So one is you can actually just compose a data set, which you purposefully go out and try and collect a balanced data set of what you identify as fake reviews and correct reviews, and it will constrain your data size, but what you do then is you train a model and then you do something called pseudo labeling, where to try and get more data like the ones that you just took so much time to label, you run eval again on unseen data. And then you take high confidence, high probability examples, and you again have a human look at it, but it's a way to speed up labeling because this is actually a big problem in applied domains. The second way is that you kind of do this mechanically in the loss function. So you re-weight samples. So you set, you kind of stratify automatically and you upweight the fraudulent examples. So the model has to pay more attention to the fraudulent examples. And that also can be quite successful. And then again, you would try and find more examples like that. But I think the best way is to deal with it in the batch itself, just because if you reweight, it might introduce interesting learning dynamics. Like you might have to adjust your learning rate or some other hyperparameters to deal with essentially higher gradients. So that's a few starting points. But the crucial thing with imbalanced data is that the imbalanced class, the smaller class, make sure it's good quality. So this is the big issue, is that because you have few examples, really pay attention to how those are labeled. Because noise in that class, noisy examples, so either mislabeled or improperly structured, is actually going to have a much bigger weight on performance than usual because you just have far fewer examples. So take the time to do the human auditing.
Thank you, Sarah. So we've got about 10 minutes to go, and one area that we're really going to talk about, I want to touch on, are areas that pertain to much about the community, Africa, where you grew up and where you've spent a considerable amount of time. Last year, and probably this year, if not for the way the world has changed. So you've interacted with the community, you've taught at Data Science Africa, you've been to the deep learning in Dabar, spoken and taught there. So my first question is how excited about this is, I know the answer to this question, but I'm going to ask it. How excited are you about the machine learning, the AI community in Africa? And a lot of people believe there's a lot of hype around AI going to solve some of our biggest problems, famine, hunger, climate change, poverty, personalized education. Are you still bullish on those views of how useful AI would be for Africa, for the community, and for our problems? So for the African community of practitioners, and for the problems that are quite prevalent in Africa right now.
Yeah, I guess there's a few questions there. So yeah, as you mentioned, I grew up in Africa. So my mom is Irish, my dad is English. They met in Sudan, and then I grew up all the way through university. They keep on moving. I now consider myself just a citizen of the world because I've since been in the US and my husband is in the US. But I still feel very close to the communities I grew up in, mainly because I think that machine learning is such an exciting opportunity. And I think there's a few layers to this. So you mentioned one, which is the perhaps problems that can be solved using machine learning, when machine learning is promising. And there, I definitely think there's really interesting problems, like anywhere that we can apply machine learning to. But we also just have, all of a sudden, a lot of data that we can leverage. So, for example, satellite imagery, thinking about how people are interacting with mobile phone data. We just have a lot more understanding of what are the patterns that we see in an economy, and how can we use that to really address some of these problems. But I think actually the area I'm most excited about is that I just think it's an incredible way for really young people to tap into a career path where a lot of your individual effort translates. And so I think this is a thing that perhaps, at least where I grew up, was quite clear, is that, Africa has traditionally been resource exporters, right? And so a lot of it is about the logistics of how do we export all these commodities. That takes a lot of existing logistics, existing resources. So you tend to see a few big logistics players, and it's hard for an individual to craft their path. I think now with technology, we're just seeing all these exciting entry points into global job markets where people can invest in themselves and show their determination and be like, this is what I want to do, and see it translate in all these interesting ways to how they can contribute. And that's exciting because it removes the inertia of a lot of these macro effects, right? Now you can have more control over your path. And that's not going to happen overnight. But technology has been more promising to, at least in my mind, especially when I go teach and when I see how myself, like I've been able to go from this little girl in northern Mozambique all the way to what I'm doing now, which is research at Google. I feel like it offers an entry point that often isn't possible in other industries. And that for me is what has really made it exciting. I think there's another question on the screen, which is, do you see the social good as a possibility in a region that's lacking access to data?
Yeah, hold on. So it's a two-part question. So this is the first part. And first of all, the person who asked this question apologized for asking too many questions, and there's no need for apologies. Please ask as many questions as possible. And for those of you who maybe your questions don't make it here, just know that I just have only two hands and two eyes. I'm trying as much as possible to bring in as many questions, and trying as much as possible to keep the questions within the frame or the segue, the sequence of narratives of the particular webinar. So there are great questions. We will come back to them. So this question on social good, so it's two parts. So do you see social good as a possibility in a region that is lacking access to data? Of course, that's my answer. At least I have an answer to the question. And one way to attract more voices to ML is attaching it to social good. What are your thoughts on the use of ML for social good, especially in sub-Saharan Africa? I would also want to say one thing right now is it's a very difficult period, with the pandemic, the lockdowns, a lot of social problems. I mean, we have friends and families, and shout out to those of us who personally, those I know, some have even spoken to today, who are really adversely affected by the COVID-19 pandemic or the economic downturn thereof. So we care about you, and we really wish we could, do more. And I think it's one of the reasons why we need more people in this space, because we have a lot of things that are going on, interesting papers being published, people analyzing data, people even trying to use AI and machine learning, to sequence new drug discoveries or analyze the vast amount of data from those who are either affected or infected in one way or the other. With that lens and this whole concept of social good, what are your thoughts on the use of ML for social good, especially in sub-Saharan Africa or in Africa as a whole, or resource-constrained environments? This could be Southeast Asia, could be Latin America. We've seen a couple of ML use cases. Some of them are very pretty documentaries about what's been done in health or with clients, but let's be a bit more specific, especially with the research you're involved in and some of your colleagues in the brain team in Accra and stuff. Well, what is that ML for social good narrative or push that you want to share or you want to let everyone know about?
Yeah, I think there's a huge opportunity for ML for social good, mainly because the truth is machine learning, the way that people think about problems is often they weigh more heavily the problems in front of them. So what's exciting about having the lab in Accra is that you are now thinking more thoroughly about the problems that you are experiencing. And so I think that is exciting. Even my research on resource-constrained environments, a lot of the reason I'm interested in it is because of essentially like the data pain that I've experienced in the communities I grew up in, knowing that data is expensive, knowing that to make these deep neural networks work, we have to make them work in resource-constrained environments. So often our motivators are driven by what we've experienced, right? And that's why I think it's so important to bring more people who are passionate about what they see and the solutions that they see into this space. And in fact, it's probably more than important, it's kind of critical. The truth is that a lot of these problems, often the solution goes wrong because there's not a domain expert in the loop. So often a lot of machine learning that seems really fancy, high test set accuracy, there's a detail in the data that no one involved realized that someone who was closer to the problem on the ground would notice and say, oh, there's a ruler in all these photographs. Going back to the example from healthcare I gave earlier, we need more people like that who are close to the data and can see patterns. And that's that second bucket that I talked about earlier, which is creativity. Creativity is still a huge part of machine learning. As I mentioned, this is recent history. Machine learning, as we know it, only really kicked off in the 1940s. So we're still in the first generation of approaches. And that's the thing, that is again why it's just an exciting time to be part of it, because so little is static and so little is known. There's so many unknowns still in how we can do this.
Fantastic. So the reviews are coming in. Awesome session. We appreciate you both at this. I see even a comment from my brother, and he had power issues. You're talking about resource constrained areas. And there's a question. I read a research paper recently about light-based TPUs, and that is 2 or 3 orders of magnitude faster than that. How do you think this will impact the future of deep learning and artificial intelligence? Okay, so we've got 90 seconds to go. So you can give a quick answer, or we can refer Fortune later to a follow-up.
I love this question.
You love this
very good question, yeah. Because
your pattern shot, I'm gonna disappear and no one's gonna see me again. So it is your answer to the question and your pattern shot that will close out this webinar.
Don't go!
The time starts now.
Wow, this feels like a game show. I'm like, oh, only 90 seconds. So this question is interesting because hardware is so important to algorithms, right? So in 2012, a lot of what happened was not that convolutional neural networks happened, but that GPUs happened. And they made it possible for convolutional neural networks to finally show themselves to be empirically successful. So hardware, which makes it easier for us to show algorithms, and particularly to scale algorithms in a powerful and efficient way, is really important. So really great question from Fortune. I do think efforts like this will impact this particular effort. It's hard to know, but thinking about light as a way to overcome like Moore's law and the decrease in chip capacity is really interesting. With that, I think I have 1 minute. Is that possible? Wow, I was very brief in my in my answer, but it's been a pleasure to be here. Thank you everyone for attending. I'm indebted because I am in the presence of a master, and I feel that I will also be waiting very patiently for the Netflix show. So better hustle on that. Let me know. Remember the small people when you get there. And with that, I will say goodbye. So thanks, everyone. I guess I'll wait for an order of whether I should leave the studio or not.
No, you don't need the studio.
I don't leave the studio.
You've got 15 seconds to crack a joke. No pressure. One joke before you go. A machine learning
joke. A machine learning joke. This is okay. So I really feel tempted to type it into GPT-3 and say, "Tell me a joke." I'll leave it for the bots. I'm not that good a comedian.
All right, Sarah, thank you very much. And thank you for everyone who tuned on the show. Please subscribe to this channel, depending on where the button is. And thank you very much, Sarah. Thank you, everyone. Bye for now. Till next week.
Who's next week?